In this video, multi-level associations, mining, multi-dimensional association rules, then constraint-based association mining will be covered. For many applications, strong associations discovered at higher abstraction levels, though with high support, could be common sense knowledge. We may find novel patterns at more detailed levels. For multi-level association, the electronic shop problem is given. The electronic store showing the items purchased for each transaction. The concept hierarchy for the items are shown in the diagram. A concept hierarchy defines a sequence of mappings from a set of low-level concepts to a higher level. The data can be generalized by replacing low-level concepts within the data by their corresponding higher-level concepts or ancestors from a concept hierarchy. As shown in the figure in the previous screen, the concept hierarchy has 5 levels, respectively referred to as levels 0 through 4, starting with level 0 at the root node for all. Here, level 1 includes computer, software, printer and camera, and computer accessories. Level 2 includes laptop computer, desktop computer, Office software, antivirus software, etc. And level 3 includes Dell desktop computer, Microsoft Office software, etc. Level 4 is the most specific abstraction level of this hierarchy. It consists of the raw data values. The concept hierarchies for nominal attributes are often implicit within the database schema. Concept hierarchies for numerical attributes can be generated using discretization techniques. Concept hierarchies may be specified by users familiar with the data such as store managers. The items at the lowest level of our concept hierarchy, it is difficult to find the interesting patterns in such raw or primitive level data. For example, Dell Studio XPS 60 notebook or Logitech VX Nano cordless laser mouse occurs in very small fraction of the transaction, though it is difficult to find strong associations involving these specific items. Few people may buy these items together, making it unlikely that the item set will satisfy the minimum support. We would expect that it is easier to find strong associations between generalized abstractions of these items, such as between Dell notebook and cordless mouse. Association rules generated from mining data at multiple abstraction levels are called multiple level or multi-level association rules. These multi-level association rules can be mined efficiently using concept hierarchies under a support conference framework. In general, a top-down strategy is employed where counts are accumulated for the calculation of frequent item sets at each concept level, starting at concept level 1 and working downward in the hierarchy toward the more specific concept levels until no more frequent item sets can be found. For each level, any algorithm for discovering frequent item sets may be used, such as a priori algorithm. Using uniform minimum support for all levels, the same minimum support threshold is used when mining at each abstraction level. A minimum support threshold of 5% is used throughout. Example for mining from computer downward to laptop computer. Both computer and laptop computer are found to be frequent, whereas desktop computer is not. When a uniform minimum support threshold is used, the search procedure is simplified. The method is also simple in that users are required to specify only one minimum support threshold. An a priori like optimization technique can be adopted based on the knowledge that an ancestor is a superset of its descendants. The search avoids examining item sets containing any item which the ancestors do not have minimum support. The uniform support approach, however, has some drawbacks. It is unlikely that items at lower abstraction level will occur frequently as those at higher abstraction level. If the minimum support threshold is set too high, it could miss some meaningful associations occurring at low abstraction levels. If the threshold is set too low, it may generate many interesting associations occurring at high abstraction levels. Using reduced minimum support lower levels, each abstraction level has its own minimum support threshold. The deeper the abstraction level, the smaller the corresponding threshold. For example, the minimum support threshold for level 1 and 2 are 5% and 3% respectively. In this way, computer and laptop computer and desktop computer are all are considered as frequent. A serious side effect of mining multi-level association rules is its generation of many redundant rules across multiple abstraction levels due to the ancestor relationship among items. For example, consider the following rules where laptop computer is an ancestor of Dell laptop computer based on the concept hierarchy and where X is variable representing consumers who purchased items in the electronic shop transactions. If rules are both mined as per the right hand side, rules 7.4 and 7.5 are mined, then how useful is rule 7.5? Does it really provide any novel information? If the latter, less general rule does not provide new information, then it should be removed. A rule R1 is an ancestor of a rule R2 if R1 can be obtained by replacing the items in R2 by their ancestors in a concept hierarchy. For example, rule R as 7.4 is an ancestor of rule 7.5 because laptop computer is an ancestor of Dell laptop computer. Based on this definition, a rule can be considered redundant if its support and confidence are close to their expected value based on ancestor of the rule. Mining multi-dimensional association rules that imply a single predicate, that is, the predicate bias. For instance, in mining our electronic shop database, we can discover the Boolean association rule. Buying a digital camera by X, then buying an recipe printer also by the X. Following the terminology used in multi-dimensional databases, we refer to each distinct predicate in rule as a dimension. Hence, we can refer the above rule as a single dimension or intra-dimensional association rule because it contains a single distinct predicate with multiple occurrences. Such rules are commonly mined from transaction data. Additional information regarding the customers who purchase the items may also be stored. Considering each database attribute or warehouse dimension as a predicate, we can therefore mine association rules containing multiple predicates such as quantitative attributes are numeric and have an implicit ordering among values. Techniques for mining multi-dimensional association rules can be categorized into two basic approaches regarding the treatment of quantitative attributes. In the first approach, quantitative attributes are discretized using predefined concept hierarchy. This discretization occurs before mining. For instance, a concept hierarchy for income may be used to replace the original numerical values of this attribute by interval labels such as 0 to 20k, 21k to 30k, 31k to 40k, and so on. Mining multi-dimensional associations, the discretized numeric attributes with their interval levels can then be treated as nominal attributes. We refer to this as mining multi-dimensional association rules. In the second approach, quantitative attributes are discretized or clustered into bins based on the data distribution. The discretization process is dynamic and established so as to satisfy some mining criteria such as maximizing the confidence of the rules mined. Because this strategy treats the numeric attribute values as quantities rather than as predefined ranges or categories. Association rules mined from this approach are also referred to as quantitative association rule. Each of these approaches are used for mining multi-dimensional association. Next is constraint-based frequent pattern mining. A data mining process may uncover thousands of rules from a given data set, most of which end up being unrelated or uninteresting to users. Users have a good sense of which direction of mining may lead to uninteresting patterns and the form of the patterns or rules they want to find. They may also have a sense of conditions for the rules, which would eliminate the discovery of certain rules that they know would not be of interest. Thus, a good heuristic is to have the user specify such intuition or expectations as constraints to confine the search space. This strategy is known as constraint-based mining. In the constraint-based frequent pattern mining, the constraints can include the following: knowledge type constraints. These specify the type of knowledge to be mined, such as association, correlation, classification, or clustering. Second, data constraint. These specify the set of task-relevant data. Third, dimension or level constraints. These specify the desired dimensions of the data, the abstraction levels, or the level of the concept hierarchies to be used in mining. Next one, interestingness constraints. These specify the threshold or statistical measures of rule interestingness such as support, confidence, and correlation. Next one, rule constraints. These specify the form of or conditions on the rules to be mined. Such constraint may be expressed as meta rules as the maximum or minimum number of predicates that can occur in the rule antecedent or consequent, or as relationship among attributes, attribute values, and aggregates. Meta rule guided mining. Suppose that as market analysts for electronic shop, we have access to the data describing customers as well as the list of customer transaction. We are interested in finding associations between customer traits and the items that customers buy. However, rather than finding all of the association rules reflecting these relationships, we are interested only in determining which parts of customer traits promote the sale of Office software. A meta rule can be used to specify this information describing the form of rules we are interested in finding. An example of such a rule is P1 of x comma y and P2 of x comma w then goes to B by uh, Office software, where P1 and P2 are predicate variables that are instantiated to attributes from the given database during the mining process. X is a variable representing a customer. Y and W take on values of the attribute assigned to P1 and P2 respectively. Typically, a user will specify a list of attributes to be considered for instantiation with P1 and P2. Otherwise, a default set may be used. The data mining system can then search for rules that match the given meta rule. For instance, following rule matches or complies with meta rule. Age of X between 30 and 39 and income of X between 41,000 and 60,000. Then he is going to buy Office software.